Oh, you mean my kids at home?
Yeah.
All right, so equilibrium is this crazy idea that things move forward and backward at the same rate. And the bulk of this next unit, the first unit in equilibrium, and the 12th chapter, is the idea that when you have things melting at 0 degrees, when water is melting, it is also freezing. For instance, I put some ice cubes in this water, and the ice cubes were distinct cubes, well, more or less cubes. And you might notice, and you've seen this before, the ice cubes have frozen themselves together. These 3 froze themselves together, and these 2 froze themselves together. So they melted in the water, and then they refroze together. That's an equilibrium. So the water was between the ice cubes, was 0 degrees, so the ice cube both melted, got smaller, and refroze back together. Pretty slick. And that's what happens when things undergoes phase changes. They do both things. They both warm and cool. They both freeze and thaw. They both boil and condense at the same time. So the title of this unit really should be State Equilibrium. Okay. We have to remember, coming out of gas laws, of course, that the kinetic molecular theory is very, very important. All matter is made of particles that are in random and constant motion. All matter. Even solids? Even solids, right? Even solids are in random and constant motion. And in the molecular world, there's a battle. There's a battle between the intermolecular forces. By the way, that means between molecules, intermolecular. There's a battle between the intermolecular forces that want to hold molecules close and the molecule's own kinetic energy, which wants to make them fly apart. Now, we learned that when we say kinetic energy, what do we really mean? It starts with a T. Temperature. Okay? So temperature is a measure of kinetic energy, of average kinetic energy. And the higher your temperature, the more kinetic energy you have. Well, if you have a bunch of water molecules that are held together by intermolecular forces, and they're pretty much stuck in position, they're just vibrating a little bit, then what state of matter do you have? Is anyone besides Carson going to be playing along today? So you have a bunch of water molecules, and they're fixed in position, and they're just vibrating around. What state of matter is that? It's solid. Yeah, it's solid. And if I warm those molecules up, they start to vibrate. And the point at which their intermolecular forces become weaker than their kinetic energy, the molecules separate. They melt. So by raising the temperature, we increase the kinetic energy of the molecules to the point where that kinetic energy becomes larger than the intermolecular forces, and the molecules will separate. They will melt. If we increase the temperature even more, the molecules will keep moving around and moving around and moving around, and eventually they have so much energy, they leave each other. They leave the liquid phase. If the kinetic energy is so much larger than the intermolecular forces of a liquid, then those molecules will enter the gas phase. So that's basically the bulk of the entire unit, is talking about phase changes, going from one phase to another phase. Using this diagram. Any questions before we jump right in? All right. Okay, I have a question for you. If I take some water, put it on the table, what state are those drops of water? Yeah, it's not a trick question, it's liquid. They're liquid. Liquid, liquid, liquid. By the end of class today, am I going to be able to see where those drops are? No, they're going to evaporate, right? Okay, now we know this. We know that liquid molecules will evaporate. If I take some water and put it on the table, it's going to evaporate. Here's the thing. What is the boiling temperature of water? Ugh. In Celsius, the boiling temperature is 100 degrees. Does this look like 100 degrees to you? But why is it that the water evaporates? you ever thought about that? This is something you could ask your parents tonight. Do the same thing, only make sure the water isn't actually boiling. Stick your finger in some water, and then put it on the table and say, you know what, Mom? That water is going to evaporate. And she'll say, yeah. And you say, what's the boiling temperature of water? And she'll say, 100 degrees, because she's learned. And you're like, but how is it that I can put my finger in water that's clearly not 100 degrees, and this water that's clearly not 100 degrees is going to evaporate? Why? Well, how would you answer? How is it that water that is clearly not 100 degrees is going to evaporate? Okay, here's the thing. If we took an average of everybody's height in their room, and let's say the average was 5 foot 10 inches. Does that mean everybody is 5 foot 10 inches? No. Does that mean people are above 5 foot 10 inches? Does that mean people are below 5 foot 10 inches? Yes. Remember how I said temperature is the average kinetic energy? Does it make sense that if you had a sample of gas at, say, 45 Celsius, that there are some of those gas molecules that actually are above 100 degrees Celsius? This is called a distribution. This is called a distribution. A distribution is like the molecules have been distributed. And the lines are the approximately number of molecules at any given temperature. So up here, we have the 100-degree line. Everything above this is at 100 degrees. Everything below this is at less. Maybe this is 0. Maybe it's not. But this is important. Any sample of gas, or any sample of water, has molecules in it that are above 100 degrees. They're moving with that much energy. Do you see them? No, you don't see them. Sometimes you see the bubbles forming a little bit as the water warms up, and this water is warming up. But you don't see them because the molecules, there's so many of them, and very, very few of them have enough energy to leave into the gas phase. But there are some. This is the average. This is a bell curve, by the way. When you say, are you going to curve our grades? This is what the teacher's supposed to use. Bell curve. 60% of you get C's. 15% of you get B's. 15% of you get D's. And then 5% get A and S. That's the bell curve. You don't want a curved test, not in this class. Because if you're like, I got an 85%, but that wasn't good as my neighbor, so I got a D. You don't want a bell curve. But this is an average. Curves are averages. This is an average. And at 25 degrees, there's still a few molecules that have enough energy to boil. At 35 degrees, there's more molecules that have energy to boil. And as I heat this water up, as we speak, it's getting warmer and warmer. As I heat this water up, this curve is constantly shifting. In a few minutes, that curve will have a hump very close to the boiling line. And we're going to start to see that there are enough molecules that they boil. Does this crazy idea make a little bit of sense? Okay, this is fairly new material. I just want to make sure we're on track here. So as I heat this up, the hump is getting further and further towards the boiling line, and eventually a large portion of the hump is going to be on the boiling line. It'll be boiling so fast that we'll actually see it boil. Okay. So if you like things written down, there's it written down. This is called a distribution. Some have an energy enough to boil, these over here, and when the high and low energies are such that when there's more high energy than low energy, then you get a phase change. When that distribution gets hot enough, gets close enough to that boiling line, then you get a phase change. Yes. What is your question?
So you're saying when you throw the water on the table and it evaporates because some of them, like molecules, know if you have like this water and put it on the table, there's some that's at 100 Celsius, but you didn't heat them up or anything.
Yeah.
Weird.
Even if your distribution is so far, it is weird. Even if your distribution is so far to the left, there's still a tiny number they're going to cross this line. Yeah. And the reason things boil faster, like warm water evaporates faster, is there are more. When you move this curve over to the right, there are more things under this line. But yeah, goofy, huh? So ask your parents to go home and say, how is it that water evaporates even though it's clearly not at 100 degrees? And they'll be like, go do your homework and leave me alone. I'm not wanting that learning stuff. Other questions before we move on? Then we move on. Okay, solids. Solids are great. Okay, so we know that the intermolecular forces in solids do exist and they're pretty strong. We also know that there's kinetic energy, but if you were to compare the intermolecular forces versus the kinetic energy of a solid, which one wins? Intermolecular forces. Again, it's a battle. It's a constant struggle between the two. So with solids, you have very low kinetic energy and very strong intermolecular forces. In fact, this is what a solid is. A solid is something that has very strong intermolecular forces and very low kinetic energy. This is something we mentioned when we did gases, just a reminder because it's awesome. The density of a solid is about 1,000 times that of gases. This is why you can make a dry ice bomb. Put a little bit of dry ice in a 2-liter bottle, seal it up. That dry ice wants to occupy 1,000 times its volume when it turns into a gas. You can totally do it. Yes?
It's like a banana is a solid, but put it in a blender, blend it up, put a lot of water to put the liquid so it's so or just mix.
It's called a suspension. It's a suspension of solid particles and liquid particles. So the banana molecules remain banana molecules.
No, yeah, I was just curious.
Yeah, it's called a suspension. Which is actually the next unit. After this, we're going to talk about suspension solutions and colloids and how we classify materials. Oh, best thing about this unit, you're going to love this, no math. Unless you count adding 273 to Celsius, then that's the only math you really have to do. Adding 273 to Celsius. Other than that, no math. Okay. Okay. So this is actually a diagram that I think is in your textbook. Actually, it is, and it totally doesn't do this justice. But the idea is you would need 10 of these blocks vertically, horizontally, and into depth into the y-axis to equal a gas. Remember how I mentioned how the density of a school goes? If there are 600 people in this school and we were a solid or a liquid, how many people would be in the school if we were a gas? 1. There'd be 1 person in the whole school if we were a gas. That's how separate gases are. Questions about solids before we move on? Okay, liquids. How would you classify a liquid's intermolecular force? I want to take a volunteer that isn't Carson. How would you classify liquids' intermolecular forces? You can raise your hand and throw something out. Less.
Not as strong as solids.
Excellent. Exactly right. Yeah, exactly right. Not as strong as solids. So liquids' intermolecular forces are not as strong as solids. How would you classify their kinetic energy? Not as low as solids. Excellent. Yeah, well done. Yeah, so the molecules are close together, but they are allowed to slide over each other. They're not fixed in place. So they are fluids. They have intermolecular forces that are still strong, but not as strong as solids. And their kinetic energy is still low, but not as low as liquid. Or not as low as solids. They're like solids, but not as much. Apologize for the contrast in colors, but liquids have cohesion. Cohesion basically means stickiness. might have heard the word adhesion. Adhesion is also sticky. So that tape is adhesive. Things that are adhesive stick to other things. Things that are cohesive stick together. Like when you are on a team, you want to be a cohesive team. You want everyone in your team to behave and think the same. So you know, like, if I kick the ball down to that guy, I know what he's going to do with that ball, because we are a cohesive team. Molecules that have cohesion stick together. Molecules that have adhesion stick to other things. You have adhesion. So you stick to the winning. When you do a belly flop into the pool, the cohesion is what hurts. The cohesion creates surface tension. When you get out of the pool, the reason you're wet is due to adhesion. Fun fact, there are some liquids that have almost zero adhesion. Mercury has almost zero adhesion. Yeah, that would be really, really hard to do. If you tried, you could walk in mercury. It's so dense that if you tried to walk on it, it would only go up to your ankles. You're like, but then when you pulled your ankles out of the mercury, you shake it off, it's going to not stick to your skin at all. Mercury vapor is poisonous in that if mercury vapor gets into your brain, it stays there for almost ever. Pretty much, yeah. Oh yeah.
No, because the metal will coat your brain and make it strong.
Yeah. But then you'll be vulnerable to magneto. You don't want that. Okay. So phase changes. Here's some words for you to learn. Some of these might be new, some of these may be like, well, duh. When you go from liquid to solid, we call that freezing. Solid to liquid, we call that melting. Liquid to gas, we call that evaporation. Gas to liquid, we call that condensation. Words that might be new, when solids go right to gas, we call it sublimation. And when gases go to solids, we call it deposition. So when we crack open a container of dry ice, that dry ice starts immediately to go to a gas, and we call that sublimation. By the way, you don't see the dry ice gas. All those vapors that come off the dry ice are tiny water molecules.
Is plasma considered one?
Not really.
No.
Yeah, plasmas and Bose-Einstein condensates are for another discussion far in the future. We focus on the three states of matter that we encounter on a daily basis. Okay, now I'm going to write some stuff on the diagram. Just so we're all on the same page. What does that mean? Right, greater than. And what does that mean?
Oh, I thought it was
Less than. Okay, so deposition. Kinetic energy, intermolecular forces. Which is bigger in deposition? When gas is becoming the solid. Intermolecular forces. Okay, so in deposition, the intermolecular forces of the gas overwhelm the kinetic energy and you become a solid. See where I'm going with this? Okay. Sublimation. I'll just do this. Kinetic energy and intermolecular forces. Which one wins in sublimation? Kinetic energy. Okay. So if a solid's kinetic energy becomes high enough to overcome the intermolecular forces, that solid can become a gas. Condensation, kinetic energy, intermolecular forces. Which one wins? We're condensing, so which one wins? Intermolecular forces. Evaporation, kinetic energy, intermolecular forces. Which one wins? Kinetic energy. If you have some liquids and you increase its kinetic energy, eventually when the kinetic energy is bigger than the intermolecular forces, it boils. Melting, kinetic energy, intermolecular forces. Which one wins when a solid melts? Wins when a solid melts? Kinetic energy. And once again, lastly, freezing, kinetic energy, intermolecular forces. Which one wins when you're freezing? Intermolecular forces. All right. So again, there's a battle. There's a battle. When one of these phase changes is happening, that means the kinetic energy is winning or losing. That means the intermolecular forces are winning or losing. Here's the crazy thing, and what's kind of new and just bizarre about this unit. You've always been told that processes go one direction. Not quite true. Processes actually go both directions. Like the ice. This ice actually refroze again while I'm talking. Well, it did, promise. Those four little water molecules refroze together. So when one of these things is happening, the other thing is also happening. That's called equilibrium. Okay. So equilibrium gets its own little symbol. I'll draw it for you. I do not have the capability to draw it in PowerPoint, unfortunately, but I show you what it looks like. So if you see this sign, that means what turned to what? It means reactants turned into products. Okay. This is the equilibrium sign. This means the reaction goes both ways. And dynamic equilibriums are everywhere. Thank goodness. If you saw Beautiful Mind, there's a very quick bit in there about John Nash's equilibrium idea, where he applied the ideas of equilibrium, scientific equilibrium, to economics. Got the Nobel Prize for it. His ideas were not new, but applying them to economics and sociology and politics was new. But scientists knew this forever. We were like, yeah, we know how this works. Dynamic equilibrium. A dynamic equilibrium works like this. A grocery store knows how much food it needs to stock through research. And the idea is, if you're going to maximize your profits, you want to bring in as much food as you sell to keep your store shelves stocked. Get the idea? So in a normal situation, Sunday afternoon, normal families, good weather, they're buying their vegetables, the grocery store is stocking the same vegetables. Buy, sell, stock, it's dynamic, it's equilibrium, it's safe. If you were in the southeast and there was a hurricane that wiped out all of the oranges, the orange population would drop rapidly, right? There wouldn't be a lot of oranges. So the people would know, or the store owners would know, they need to get as many oranges as possible because there's going to be a drop. They know there's going to be a drop. There's not going to be very much in the future, so you want to buy as much as possible. Does that idea make sense? Similarly, if you knew there was a hurricane and your parents knew there was a hurricane coming, you'd want to stock up. So you're going to stock up on soup, all sorts of canned goods that last a long time, or canned vegetables or something. You want to stock up, stock up, stock up. So that drops the population of soup. So the store owners have to buy more soup. Okay? So a dynamic equilibrium is everything is in sync, like a shopping mall. If you had a shopping mall and there were 4,000 people going in during this busy time, we would ideally hope 4,000 people are going out during the busy times. Make sense? That's equilibrium. It's dynamic, there's movement, but hopefully the movement is equal. Okay, so freezing, melting, occurrence, and evaporation kind of at the same time. Same rate. Same rate. Meaning, as this ice melts, it's also refreezing. As this water is boiling, it's also recondensing. Boiling is tricky, though, because as it's boiling, it's actually leaving the container. But in a dynamic equilibrium with states, the two things are happening at the same time. Melting and freezing is happening at the same rate. The same rate something melts, something freezes. Condensation and evaporation, at the same rate something condenses, something evaporates. equilibrium going on in your body right now. You have chemicals in your body that keep you from dying when small things happen to it, like temperature changes or viruses or bacteria. Your body likes to stay in equilibrium. Biologists use the term homeostasis. Everybody's got a different term for it. Okay. Is there any questions about this before we move on to something else? All right. Le Chatelier's principle. Le Chatelier's principle is brilliant. Okay. Basically, Le Chatelier's principle says this. Are you ready? You're writing Le Chatelier's. I'm seeing L-C-H-A-T-E. Okay.
Le Chatelier.
Yeah, Le Chatelier. Because he's French. He can spell it however he wants. Okay. I'm going to give you my interpretation of Le Chatelier's principle. Are you ready? Whatever you do to the EQ, I will undo to redo the EQ. Le Chatelier's principle goes like this. Whatever you do to the EQ, I will undo to redo the EQ. Officially, Le Chatelier's principle is like this. Any stress applied to an equilibrium, the system will react to resist that stress. So whatever you do to the EQ, I will undo to redo the EQ, or a system in equilibrium will always act to resist a stress. I hope I can do this without, I'm going to turn the lights on just because it's easier to see. What color is the liquid in this bottle? Purple.
Violet.
Violet. Okay, it's violet. So everyone who said violet, raise your hand. Or purple, raise your hand. Okay, looks like most of you said purple or... Yeah. I'm sorry, you're wrong. It's actually blue. And everyone who's... So what color is this now?
It looks like purple.
It's blue. Okay.
Violet.
Blue, violet. Okay. The ice water takes a little bit longer, but it is still fun. This is a really fun chemical. This is chromium chloride. Chromium chloride creates an equilibrium with a complex of itself that where one of them is red and one of them is blue. At room temperature, it's purple. When it's cold, it turns blue. I'm sorry, when it's hot, it turns blue, and when it's cold, it turns red. And it's going to take a long time because the ice is melting. But we're back to our purple. This is NO2 and N2O4. See the colors? I'm going to put one in the hot water, and hope it doesn't crack, and one in the cold water, and hope it doesn't crack. These two chemicals have a fun little equilibrium. Works like, actually it's written right up here. So 2NO2 is in equilibrium with N2O4. It should make sense that you don't have to do anything, you have to add any chemicals. These two things have the same number of chemicals involved. NO2 is a funky dark color, and N2O4 is this fun tannish color, or colorless. It's yes. So I'm heating this one up, and cooling this one down. Trying anyway. Pretty soon they're going to change color. Now here's how Le Chatelier's works with a chemical equilibrium. Are you ready? If you take away something, Le Chatelier's is going to work to recreate it. If you add something, Le Chatelier says the equilibrium is going to take away what you add. So I like to say this. Up, over, down, 2. I like to say up, over, down, 2, and I'll show you what I mean by this. Here's our equilibrium. By adding heat, the system, I increase the right side. By adding heat, I increase the right side. the system is going to shift the equilibrium that direction to remove some of the right side. By adding heat, I upset the equilibrium. I stressed the equilibrium. By increasing more right side, the system's going to shift this direction to create more left side by sacrificing the right side. Does that make sense? So, which one is the hot one? Oh, by the way, if you want to see, you can hopefully see they're a little bit darker now. This one's a little bit darker. It isn't boiling. I kind of wish it was boiling, but it's not boiling. Which one's the hot one? The NO2 or the N2O4? NO2. So you can think of it this way. N2O4 plus heat makes NO2. Or NO2 yields N2O4 plus heat. So this is the equilibrium. By the way, I have to write this. I have to write the equilibrium sign that way. When I add heat, I create stress. Now there's more right side. And I force the equilibrium to the left. Does that idea make sense? Up and over. Yeah, on the cold side, with the ice water that's not all that excellent, if I take away heat, I reduce right side, the equilibrium will shift to recreate it. By reducing the right side, by stressing the system, by reducing the heat, I cause the equilibrium to shift this way. Does that idea make sense? Okay, same thing happens when you put a gas under pressure. If you put a vapor under pressure, if you increase the pressure, the equilibrium shifts by creating a liquid. Does that make sense? And if you reduce the pressure, the equilibrium shifts by turning a liquid into a vapor. Does that make sense? All right. This water is not boiling. Thank goodness. Well, that is, but this water is not boiling. I can hold it in my hand just fine. We're getting the cameras on. Okay, so I'm going to squirt it at you. Everybody got goggles on? No? Okay. Watch this. Is this water boiling? How about now? It's boiling now. Is it boiling? How about now? What did I do to those little gas molecules above the liquid? What did I do to them? I reduced the pressure. And the liquid wanted to become what? A vapor. Ta-da!
But is it hot?
Well, it's warm, but it's certainly not hot. You can do it yourself.
So, like, is it really boiling then?
Uh-huh. It's really boiling.
What do I do?
You got to pull really hard on the plunger. So, warm, but not boiling. You can certainly hold it. You pull on the plunger, you reduce the pressure, and now the equilibrium says, I want to be a vapor, and it starts boiling. Pretty slick, huh? You can do this too. I'll throw it in the back. You can play with it. Okay, any questions about Le Chatelier's principle? This is a very powerful principle. Very, very powerful principle.
Question.
Okay, vapor pressure.
Mr. Byron,
Yes.
would that be able to happen only with that warm water?
Well, the warm water makes it easier. And I'll explain why right now. I could do it with the cold water, but I have to create a lot more pressure than I can put in the the syringe. So vapor pressure occurs because that little triangle, remember the diagram, the distribution, that little triangle at the bottom? All liquids have a few molecules that want to get into the gas phase. All liquids have a few molecules that really want to be in the gas phase. So vapor pressure is how much oomph they have to get themselves into the gas phase. Now, it should make sense that the higher your temperature, the higher your kinetic energy, the faster your molecules, the higher your vapor pressure. You can think of water molecules like toddlers at a daycare. If they're hot, they're moving really fast, they're all juiced up or sugared up, eventually they're going to overwhelm the daycare and they're going to get out in the street.
What?
You got to keep the toddlers nice and cold so they move slow so the daycare the daycare can control them and they can stay out of the street. In my analogy, the daycare workers are what? The atmosphere. They're tired, yeah. They're the atmosphere. As long as the atmosphere is pushing down on my hot water, this water is not going to boil until it overwhelms the atmosphere. The point at which this hot water has more kinetic energy, has more vapor pressure than the atmosphere pushing down, it starts to boil. We're going to see it boiling when the vapor pressure is higher than the atmospheric pressure. And that's what's going on in the syringe. When you pull on the syringe, you take the atmosphere away, you reduce the atmosphere inside the container, and now the vapor pressure is larger than the atmosphere. And when the vapor pressure is larger than the atmosphere, it boils until the vapor is the atmosphere. You might notice it stopped boiling after a few seconds. So, volatile liquids are liquids that have very high vapor pressures. Some liquids are more volatile than others. If I had ether or methanol, I could actually do that syringe experiment with room temperature methanol and room temperature ether. Because they're extremely volatile. Ooh, yeah. So now that these things have had time to heat and cool, you should be able to see the significant temperature change. Get in there, you. You're going to turn red eventually. They might break, yeah. But yeah, let's give it a shot. I'm hoping, again, I've used this for, well, I've used this for 5 years, so it's had a good run. Okay, I think we're out of the woods. But yeah, so I put the hot one in the cold and the cold in the hot. So eventually this one's going to get lighter and this one's going to get darker. Basically, we're gonna kick Le Chatelier right in the butt and have it switch back. Okay, questions? All right, we're almost done. Phase diagrams. Phase diagrams are a really handy tool that say, this is the phase of matter you will have at this temperature and this pressure. A very, very handy tool. It says, based on the temperature you have and the pressure you have, this is the state of matter you will have. You need to do the following two things. You're going to do this in tomorrow's activity, in tomorrow's lab. You need to draw a phase diagram based on data, and then use a phase diagram to determine a state at a pressure and temperature. Now, this particular phase diagram is a material that at 101 kilopascals, in other words, atmospheric pressure, and 100 degrees, the material goes from liquid to vapor. At atmospheric pressure and 100 degrees, the liquid goes from liquid to vapor. At atmospheric pressure at 0 degrees, the liquid goes from, or the substance goes from liquid to solid. What do you think this is the vapor pressure for? It's water. It's water. So right now, this is not 100 degrees, but it is at atmospheric pressure. So atmospheric pressure, I'm probably about 80 degrees. So right here, the prevailing compound is going to be a liquid. The moment I get to 100 degrees, then I'm going to enter the vapor area. And here's why phase diagrams are super useful. Anything on the line is the equilibrium between those two phases. Yes? The critical, that's the point I honestly don't know. I honestly don't know what the critical point is. It's something happens beyond that point where it just stays gas. I don't know.
Something extreme.
Yeah, you'll have to look it up. I can't. I failed you. I apologize.
No, you didn't.
So anything on the boiling line, when you're at this line here, you have liquid and gas in equilibrium. So any temperature pressure combination that puts you on this line means you have liquid and vapor at equilibrium. So when you are at 1 atmosphere and 100 degrees, the liquid is boiling, but there are both liquid and vapor present. When we're on this line, you have solid-liquid equilibrium. You're at equilibrium between the solid and the liquid. And then pretty cool, this point down here, where all three come together, that's called the triple point. Triple point, another diagram, nope, okay. So this is called the triple point, where all three phases exist in equilibrium. There's a really cool YouTube about the triple point of nitrogen. I strongly recommend you watch it. It's really slick. The triple point of liquid, solid, and gaseous nitrogen. Yes?
It says it's the point of the substance which is the highest temperature and pressure which a gas and liquid coexist equally.
Okay, so the critical point is the highest temperature and pressure where both liquid and gas can exist together. So this equilibrium stops right here, and then everything else is probably gas. Very good. Okay. So that's all you need to do. You need to be able to read a phase diagram and know what phase or phases are present, and you need to be able to construct a phase diagram with raw data. Any questions? All right, good chat.